Hello everybody, we're getting ready to do lesson 8.5 of Pre-Calculus Math Part 1 today, classwork lesson. And today's lesson you will have 8 points on your notebook and 60 points on your classwork sheet, which you should have in front of you now. If you don't have classwork sheets, email me for those. Students in my classroom, name, date, period. If you're a homeschooler or you're online, put your due date here. 8.5 Part 1, Counting Principles. So today's bell work, teachers, students, here's today's bell work. Solve the equation. Solve these equations here. Round your answer to 3 decimal places if necessary. Teachers, pause your video for about 5-6 minutes and I'll see you back for the solutions. Okay, welcome back for today's bell work solutions. We have log base 2x minus 3 equals 5. So what would be our solution for this situation here? We're going to make it all 2 to the log base 2x minus 3 equals 2 to the 5. And this will become 2 to the 5 will equal x minus 3. And then we continue to solve for x. We move this over here. X will equal 35, 2 to the 5 plus 3 will equal x, etc. And then down here we will use our natural log e to the x over 3 equals natural log 16. This becomes x over 3. X equals 3 natural log 16, which when you crank it out on your calculator becomes 8.318. Today's lesson in your notebook, students, have your notebook guide out for this. Simple counting problems. The last 2 sections of this chapter present a brief introduction to some of the basic counting principles and their application to probability. In the next section, you will see that much of probability has to do with counting the number of ways an event can occur. The following 2 examples describe simple counting problems. Let's go into some counting issues here. Selecting pairs of numbers at random. 8 pieces of paper are numbered from 1 to 8 and placed in a box. 1 piece of paper is drawn from the box, its number is written down, and a piece of paper is returned to the box. Then a second piece of paper is drawn from the box and its number is written down. Finally, the 2 numbers are added together. In how many different ways can a sum of 12 be obtained? So this is what's called a counting problem. To solve this problem, count the number of different ways that a sum of 12 can be obtained using 2 numbers from 1 to 8. Okay, so our first number here could be 4, 5, 6, 7, and 8. And then our second number here could be 8, 7, 6, 5, and 4. Each of these is a sum of 12. So how many ways have we got here? From this list, you can see that a sum of 12 can occur in 5 different ways. So let's do this now. We have our guided practice here. Determine the number of ways in which a computer can randomly generate 1 or more such integers or pairs of integers from 1 through 15. Number 9 here, a pair of integers whose sum is 20, and then yours down here, students, is an integer that is divisible by 4. So from here, and these again are from 1 to 15, so take that into consideration there. For number 9, our solution here is sum is 20. We have 5 is 15, 6 plus 14, 7, 13, 8 and 12, 9 and 11, 10 and 10, 11 and 9, 8, 12 and 8, 13 and 7, 14 and 6, and 15 and 5. So we have 11 ways of 1 through 15 whose sum will be 20. And do something like that down here, students. Let's do another one. Selecting pairs of numbers at random. Again, 8 pieces of paper are numbered from 1 to 8 and placed in the box. 2 pieces of paper are drawn from the box at the same time, and the numbers on the pieces of paper are written down and totaled. In how many different ways can a sum of 12 be obtained? So now we're looking for a sum of 12. from pieces of paper that are numbered from 1 to 8. So to solve this problem, count the number of different ways that a sum of 12 can be obtained using two different numbers from 1 to 8. So first number will be 4, 5, 7, and 8. And then our second number will be 8, 7, 5, and 4. So we have a reverse sequence here of ascension and descension of that selection there. So a sum of 12 can be obtained in 4 different ways here. So what about it? Well, now we got a different counting problem here. So again, we're going to go from 1 through 15. A pair of distinct integers whose sum is 20. We'll try that again. And then an integer that is divisible by 3 from 1 through 15. So from 1 to 15, whose sum is 20, you got again 5, 15, 6, 14, blah, 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 blah. So there's 10 ways that you can add integers of 1 through 15 that will become 20. And then students, this is yours down here. Page 6 here. The difference between the counting problems in examples 1 and 2 can be described by saying that the random selection in example 1 occurs with replacement, whereas the random selection in example 2 occurs without replacement. So we're not replacing numbers, which eliminates the possibility of choosing 2 6s. So when you're doing without, you can't choose 6 twice. The difference between the counting problems in examples 1 and 2 can be described by saying that the random selection in example 1 occurs with replacement. So again, to reiterate this, it occurs with replacement, whereas the random selection in example 2 occurs without replacement. So that's a big difference there, which eliminates the possibility of choosing 2 6s. So I repeated myself here for that's all the difference in the world and counting problems. So the fundamental counting principle, examples 1 and 2 describe simple counting problems in which you can list each possible way that an event can occur. When it is possible, this is always the best way to solve a counting problem. However, some events can occur in so many different ways that it's not feasible to write out the entire list. In such cases, you must rely on formulas and counting principles. The most important of these is the fundamental counting principle, and this is it here. Let E1 and E2 be two events. The first event, E1, can occur in M1 different ways. After E1 has occurred, E2 can occur in M2 different ways. The number of ways that the two events can occur would be M1 and M2. So with two events can occur in two different ways, basically. So let's see how that will work. Using the fundamental counting principle, how many different pairs of letters from the English alphabet are possible? So there are two events in this situation. The first event is the choice of the first letter. And then the second event is the choice of the second letter. Because the English alphabet contains 26 letters, it follows that the number of two-letter pairs would be 26 times 26, right? 676. So, okay, let's try a similar issue here. A customer can choose one of 4 amplifiers, one of 6 compact disc players, and one of 5 speaker models for an entertainment system. Determine the number of possible system configurations. Well, and then this is yours down here, students. So for this one up here, audio engineering, amplifiers, you got 4 choices, disc players 6, and then speakers 5. So you just multiply these together and you get 120 different ways, different choices of compiling a stereo system, right? Yes, it really is that simple. Using the fundamental counting principle, telephone numbers, say, in the United States currently have 10 digits. The first 3 are the area code and the next 7 are the local telephone number. How many different telephone numbers are possible within each area code? Note that at this time, a local telephone number cannot begin with 0 or 1. Okay, so we can eliminate those two. So because the first digit cannot be 0 or 1, there are only 8 choices for the first digit. For each of the other 6 digits, there are 10 choices. So here's your area code, and then this will be your local number here. So we have 8 choices here, 10, 10, 10, 10, 10, okay? So we're trying to find, in the next 7 are local, how many different telephone numbers are possible within each area code. So we can make that. So to come up with that number, so the number of local telephone numbers that are possible within each area code is 8 times 10, 10, 10 would be 8 million here. So you just multiply the maximum amount together, and then this is what you come up with for the amount of local telephone numbers possible. So in 2010, the state of Nevada had 2 area codes. Using the information about telephone numbers given in a previous example, how many telephone numbers could Nevada's phone system have accommodated? And then down here, students, this is like a real similar problem down here. But for this one up here, the way we would come about that would be 2. We have 2 area codes, and then we just do our same product here from the previous example, and we just double that number to 16 million numbers would be possible with 2 area codes. Permutations. One important application of the fundamental counting principle is in determining the number of ways that n elements can be arranged. And this time it will be in order, just not random. An ordering of n elements is called a permutation of the elements. And the definition of a permutation of n different elements is an ordering of the elements such that one element is first, one is second, one is third, and so on. Well, let's get into this a little bit further here then, okay? So finding the number of permutations of n elements. How many permutations of the following letters are possible? So we have this situation here, A, B, C, D, E, F. How many permutations are possible from this list of numbers here? Consider the following reasoning. So the reasoning that we would go through to find the permutations would be our first position here, which would be A, any of the 6 letters. So that'd be, for our first position, be any of the 6. And then our second position of our list would be any of the remaining 5. And then our third position would be any of the remaining 4 letters. And then our fourth position would be any of the remaining 3 letters. So this is kind of like the walkthrough on this. Fifth position would be either of the remaining 2 letters. And then our last position, the sixth position, would be the one remaining letter. So you would do that. That would be just the walkthrough of the reasoning behind finding permutations. So having that, the number of choices for a 6th position are as possible. So here's our 6 positions here. So permutations of 6 letters, 6, 5, 4, 3, 2, 1. The total number of permutations of the 6 letters is 6 factorial. And we've gone through factorial before. The way that you calculate this is by using factorial. So 6 factorial will come out to 720 different ways or different permutations of those 6 letters. And how many ways can 5 children posing for a photograph line up in a row? And then this is yours down here, students. But for this one, how many different ways can 5 children pose for a photograph? So of course it'll be 5 factorial, which is 120 ways. And that is 8.5 part 1 of pre-calculus math. Here's my email, animatedpowerpointmathvideo@aol.com, for course materials or questions. Thank you.